Hello everyone. In this video we will talk about central force motion. So we are going to study central force motion, and we will try to derive the equation of central force motion in this video, and then we might also discuss various types of problems that come in central force motion. So let's start. The main idea of central force motion is that, let's say we are studying some objects in three-dimensional, and there are two objects. Let's call them M1 and M2. So these are the masses of the two objects, and let's say they are represented by these two vectors, which are vector R1 and R2. Our first goal would be to derive the equation of motion of these two objects, and for that we can write the kinetic energy. So the kinetic energy of the objects of this whole system is going to be half m1 r1 dot squared plus half m2 r2 dot squared. Okay, that's the kinetic energy. And the potential energy, because this is a problem of central force, the idea is that the force only depends on this relative position of the two objects. So central force is defined by a force which is between two objects, which acts along the essentially the line joining the points. So in this case, this line joining the points would be here. Let's call it R equals R2 minus R1. We can call it R2 minus R1. That's our vector which joins these two objects. So it will look like this. R2 minus R1 will give me this vector. Okay. Now, once we have this this kinetic energy and the potential energy, we can write down, of course, the Lagrangian. But you will see that the Lagrangian here will depend on R1 and R2. But what we are interested is R1 minus R2. So the goal in this case is, our goal, as we have studied in previous classes, is to write a Lagrangian that does not depend on some variables. Because if we can find a Lagrangian, let's say, which somehow does not depend on a particular variable, then del L by del of that variable is going to be 0. And if you use your Euler-Lagrange formulation, which says that d by dt of del L by del Q dot equals to del L by del Q, that's our Euler-Lagrange equation. And if del L by del Q equal to 0, then d by dt of del L by del Q dot is going to be 0, which means that the del L by del Q dot is going to be a constant. Okay, and this is of course called a cyclic coordinate, and our goal is to first convert this kinetic energy, this potential energy, and this Lagrangian in a coordinate where we can find more and more cyclic coordinates. So that's what we'll try to do, which will simplify this problem significantly. Right now there are three variables for R1, three variables for R2, so x, y, z for R1, and similarly for R2. So here we are studying, in some sense, six coordinates, right? Six coordinates. And if we try to write the equation of motion in this form, we will have six coordinates to, in some sense, keep track of. So we will reduce it, or our goal will be to reduce it to as few coordinates as possible. And to do that, what we will do is we will take this vector R R is our center of mass. So you might remember that center of mass is defined as m1r1 plus m2 r2 divided by m1 plus m2. Okay, that is the definition of our center of mass. And we also know that this position vector that connects the two objects is r equals r2 minus r1. Okay, so now that we have these two things, what we can do is we can solve r1 and r2 for capital R and small r. So that will be our first goal. So we'll do a coordinate transform essentially going from r1, r2 to capital R and small r, and we will see how it changes our kinetic energy and potential energy. So let's first do our coordinate transformation. It's not very hard to do. Here we have r equals r2 minus r1. So we can use this equation to write r2 equals r plus r1. Okay, and now we can substitute that in our first equation, which will give r capital R equals m1 r1 plus m2 r plus r1 divided by m1 plus m2, or we can further write is as m1 r1 m2 r1. So we have an m1 r1 here and also an m2 r1. So we can write m1 plus m2 r1 divided by m1 plus m2, plus we have a m2r divided by m1 plus m2. And you can see that these two cancel, and now so we have essentially r capital R equals r1 plus m2r by m1 plus m2. If you just rearrange, you can see that r1 will become capital R minus m2r divided by m1 plus m2. Okay, so this is our r1. Similarly, you can get r2. I'm just going to write down the answer here. It's not very hard to get. You do the same idea. So here we had r2 equals r plus r1. Now you can use this equation again. You can use this equation again to write r1 equals r2 minus small r, and then you substitute it in the capital R equation here to get r2 would come out to be capital R plus m1 r divided by m1 plus m2. Okay, this would be your two vectors. So now we have written r1 and r2 both in terms of capital R and small r. And what the next job is to take these things and substitute in our kinetic energy and potential energy. So to do that, we need r1 dot and r2 dot. And it's not very hard to see that r1 dot and r2 dot are simply going to be capital R dot minus m2 r dot, excuse me, divided by m1 plus m2, and r2 dot is going to be capital R dot plus m1 r dot divided by m1 plus m2. Okay, now we need r1 dot squared and r2 dot squared. So let me write that down here. So r1 dot squared is going to be capital R dot minus m2 r dot divided by m1 plus m2 squared, which will give me capital R dot squared minus 2 m2 r dot 2m2 r dot capital R dot divided by m1 plus m2 plus m2 square r dot squared divided by m1 plus m2 squared. Okay, and r2 dot squared is going to be again capital R plus m1 r divided by m1 plus m2, the whole thing squared, which will give you capital R dot squared plus 2m1 r dot capital R dot by m1 plus m2 plus m1 square r dot squared divided by m1 plus m2 whole square. Now that you have r1 dot square and r2 dot square, we are actually interested in the quantity, the kinetic energy, which is half of m1 r1 dot squared m2 r2 dot squared. So let's write that down. So what we need is, let's write that down. We need is half of m1 r1 dot squared plus half of m2 r2 dot squared. Okay, so what is half of m1 r1 dot squared? We already have r1 dot squared, which is here. So let's write what would be half of m1 r1 dot squared. That will give you a half of m1 capital R dot squared minus 2 m1 m2. So m1 comes from here, m2 comes from this expression over here, this expression over here. So which will give you 2 m1 m2 r dot capital R dot divided by m1 plus m2, and the third term will be m1 m2 squared r dot squared divided by m1 plus m2 squared. Okay, and we do the same thing for m2 r2 dot squared, which will give you half of m2 r dot squared. There should be a 2 here coming from the half, and this 2 should cancel. You will get a 2 m1 m2 r dot capital R dot by m1 plus m2. There should be a half plus you will get m2 m1 squared r dot squared by m1 plus m2 whole squared. Now because we have to do for the kinetic energy is given as half of m1 r1 dot squared plus half of m2 r2 dot squared. Because we are doing the addition of these two terms, it essentially means we add this term and this term together. Okay, now because we are adding these two, and you can check that the term in the middle, which comes with a positive and negative sign, they're exactly the same, so they cancel. Oh no, I made a mistake here. I should write down m1 m2 r dot. Okay, so these two terms cancel, and you will see that here you have a half of m1 capital R dot square, half of m2 capital R dot square, which can be written as half of m1 plus m2 r dot squared. Okay, and then finally we have a m1 m2 squared r dot squared divided by 2 m1 m2 whole square. And if you just add them together, you will see that there will be a term that will comes out. So in both these terms you will get a half m1 m2 r dot squared. That is common to both. You had a m1 m2 r dot square in the first term and the second term, and at the bottom you will get m1 plus m2 squared, and what would be remaining would be m1 plus m2. Okay, and one of these m1 plus m2 will cancel with the m1 plus m2 in the denominator, so you can cancel these things, and eventually your kinetic energy essentially becomes half of m1 plus m2 r dot squared plus half of m1 m2 by m1 plus m2 small r dot squared. Okay, this is your kinetic energy. And remember, your potential energy was something which depended on r2 minus r1 vector. Okay, but r2 minus r1 vector is simply our relative position vector r. Okay, so if you now write down the Lagrangian, you see that the Lagrangian can be written as half of m1 plus m2 capital R dot squared plus half of m1 m2 by m1 plus m2 r dot squared minus v of r. Okay, and you can clearly see that this Lagrangian is of the form L of r dot small r and small r dot. This does not depend on r. So since this Lagrangian does not depend on r is a cyclic coordinate, and we can write down the equation of motion for r, which will simply be del L by del r dot equals to a constant. Okay, remember our Euler-Lagrange formulation, as we discussed earlier, is that if the Lagrangian does not depend on a particular coordinate, then del L by del Q equal to 0. So in our Euler-Lagrange equation, d by dt of del L by del Q dot equal to del L by del Q, because del L by del Q equal to 0, del L by del Q dot is going to be a constant. So we use that idea here to see that del L by del R dot in this case is going to be a constant, which will give you m1 plus m2 r dot equal to a constant. And this is nothing else, this is just a restatement of conservation of momentum. Conservation of momentum, which says that the total mass times the center of mass velocity equal to a constant. So the center of mass is moving with a constant velocity. This is our conservation of total momentum of the system. Again, this makes sense because the system that we are studying is just two masses which are interacting with each other, but there is no external force on the system. So since there is no external force, the net momentum of the whole system must be conserved, and that is what we have observed here. Okay, so now we have taken care of the R part, or this part in our Lagrangian, and we have realized that this motion is essentially the center of mass moves with a constant velocity. Now we can look at the other part. So let's just modify our Lagrangian, and we are just going to focus on the second part, which is going to be half of m1, half of m1 m2 by m1 plus m2 r dot squared minus v of r. Okay, that is our Lagrangian, which we are now concerned with. Now, before we move further, there are a few things that needs to be discussed. The first thing is that you can see that if you look at this Lagrangian or this kinetic energy, you can think of as the kinetic energy is divided into two parts. One part is the kinetic energy of the center of mass, and then there is this additional term, right? There's this additional term, and this additional terms comes with a very specific form of mass, which is m1 m2 by m1 plus m2, and this mass is called the reduced mass. Okay. And so what you can think of this system is that earlier we were studying the system of two masses, m1 and m2, which were moving in some sense independently under the central force. But now, after we have removed the center of mass, which was here, so you can think of this problem as, let's say the center of mass is moving with a constant velocity, or the center of mass is at rest. Let's say that's the easiest thing to think about. The center of mass is at rest. Then we can imagine this problem as a problem in which we are studying some mass. So this mass is going to be this reduced mass. We're studying the motion of this mass, which is under a force where this mass is located at this point, which has this point has a position vector r, its mass is m, and it experiences a force or a potential with respect to the second, wherever the second mass was, so wherever m2 was. So you can think of that the whole problem, which is a two object problem, has now been reduced into a one object problem where the object has a reduced mass mu and it moves with respect to the other mass, okay, which is here, origin, okay. And the rest of in the rest of the problem, what we do is we study this vector r vector, assuming that it has a reduced mass mu, and this reduced mass mu is defined as m1 m2 by m1 plus m2. Sometimes it's also written as 1 over mu equals 1 over m1 plus 1 over m2. Both of them are exactly the same definition. You can use any one that you like. Okay, now that we have this, we will do a few more simplifications to study this problem. Till now, we are assuming that this vector r, this potential v of r, depends on the vector r. Now what we are going to do is we are going to make even one more simplification or an assumption where we say that the potential does not depend on the vector r but only on the magnitude of r. So what that means is that if you think in terms of the two object system, what matters is only the distance between the two objects, or only the distance from the origin to the mass mu, okay, not the vector, only the distance which matters. And this is typically the case for gravity, where the gravitational potential is g m1 m2 over r, right? Also, the electrical potential is k q1 q2 over r, or if you have a spring harmonic oscillator, the potential energy is half of k r square, right? So all these things only depend on the magnitude. So it makes reasonable to have this approximation. So we are going to make this approximation and then write our Lagrangian in terms of this approximation. Another thing that you have to realize is once you write um, this problem in terms of this vector r, um, this vector um, because now we are just thinking of an object which is moving with respect to, let's say, the origin, and there is no other force in the world. The only force is whatever comes because of this origin on this object mu, right? This means that the problem is spherically symmetric. Okay, so this problem is actually spherically symmetric. Spherically symmetric. Okay, and since the problem is spherically symmetric, and uh, there's no other force acting on this problem. This spherical symmetry, as we have studied earlier, symmetry leads to conservation, and the quantity which the spherical symmetry gives us here, which is conserved, is the angular momentum. Angular momentum. The angular momentum of the system is conserved. Okay, the angular momentum of the system is conserved. And since the angular momentum is conserved, what we can do is, let's say there is some angular momentum vector. So angular momentum has some vector, and then because the angular momentum is conserved, this vector is going to point in the same direction always, right? And what we are going to do is, you can see very easily that this angular momentum vector, which is defined as L r cross p, right? Where p is the momentum, r is the radius vector. You can argue yourself that because the angular momentum is conserved, so angular momentum points in a particular direction, and this radius vector, whatever that radius vector is, that must point in a plane which is perpendicular to the angular momentum. So if this is the angular momentum, the radius vector must lie in a plane. So there could be a plane which is perpendicular to the angular momentum, and this radius vector must lie in this plane somewhere, and it will always lie in this plane. So it's not going, as the radius vector changes because of the central force, it will always be in this particular plane. It was always going to be perpendicular to L. So we can essentially study this central force motion in two dimensions, in only two dimensions. Okay, we only need two dimensions to study the central force motion. So let me draw this once again. Let's say this is our three-dimensional space. Let's choose the angular momentum to point in the same direction as z. Okay, we can always do that. We can always just choose the z direction to be along the angular momentum. In that case, the sorry yeah so in that case, the r vector, or the radius vector, must be in the xy plane, because it has to be in a plane which is perpendicular to z direction, or to the angular momentum direction. So this is your r vector, and all we need to know in some sense is what is the magnitude of this r vector, and what is the angle of this r vector in this plane with respect to, let's say, the x-axis. So we have converted our problem, which was, remember, it was 6 different variables, x, y, z for r1, x, y, z for r2. We first reduced it to understand that capital R, which was our center of mass that was moving with a constant velocity, and now after that we have now further reduced it that there are only two variables of interest, which is the radius vector and the angle. And we are going to write our Lagrangian. So now that we write our Lagrangian, half of m r dot squared, or half of mu r dot squared, sorry, half of mu r dot squared minus v of r. Now we have specified this r is in this plane, in this xy plane, and the only thing which we care about are the radius vector and the angle. So now if you look at this three-dimensional space from looking downward from the, let's say, the z direction, then you will only have x and y, because we don't actually need to worry about the z direction or the z direction, because that is always fixed. So we only care about the radius vector, which has a magnitude r and this angle theta. And now that it has this magnitude r and angle theta, you can clearly see that the Lagrangian can be written as half of mu r dot squared plus r squared theta dot squared minus v of r. You might ask, how did I get this? There are many ways to figure out how r dot squared, the vector r dot squared, how does that turn into r dot square plus r square theta dot square? Well, the simplest way to do it would be, we know that if this is the vector r, you know that r dot squared is simply x dot square plus y dot square, right? And x would be equal to, x is equal to r cosine of theta, and y is equal to r sine of theta. So x dot is equal to r dot cosine theta minus r sine theta theta dot, and y dot is equal to r dot sine of theta plus r cos theta theta dot. And when you square and add, you will see that you will get r dot squared equals r dot square vector is equal to r dot squared plus r squared theta dot square. Okay, you can see that. I'm going to leave you that as an exercise. So our Lagrangian now is much more simpler. It depends on the magnitude r, the theta dot squared, and v of r. And again, the interesting point is that now this Lagrangian, you can see again, this Lagrangian does not depend on theta. So since it does not depend on theta, using again the Euler-Lagrange approach, you can see that d by dt of del L by del theta dot would be equal to del L by del theta, where this is our Euler-Lagrange equation. And in Euler-Lagrange equation, so this is our Euler-Lagrange equation. And because the Lagrangian does not depend on theta, del L by del theta is equal to 0, which means that del L by del theta dot equals to a constant. And what is del L by del theta dot? So in this Lagrangian, in our Lagrangian L, del L by del theta dot will give you mu r square theta dot equals to a constant, and this constant is nothing else but the magnitude of our angular momentum. So remember, our angular momentum was conserved, and the magnitude of that angular momentum is this quantity here. And we will use this quantity, we will need this quantity later. So that's our equation for the angle theta. Now that we have taken care of theta, we can actually, in fact, what we can do is we can write the Lagrangian, in terms of r only. So it will become half of, half of mu r dot squared plus, in place of theta dot, I'm going to use L over mu r squared, which will give us, if you do this correctly, it will give us L square over mu square r squared minus v of r. So this is our Lagrangian only in terms of r. So we have now reduced the Lagrangian to a function that only depends on r and nothing else. So this can be used to find our equation of motion. And the equation of motion is going to be d by dt of del L by del R dot equals to del L by del R. So let's do that. So d by dt of del L by del R dot. So in this Lagrangian, the only place where we get an R dot is here. So we will get a mu, R dot equals del L by del R. Now del L by del R, we have two terms that depend on R. One is the term L square by mu square R square, and the other term is V of R. So we can write, when you differentiate the first part, you will get an L square by mu r cubed minus L square by mu r cubed, and you will get a minus of del V over del R. Okay, that is our equation of motion. We can simplify a little bit further. This will give you mu r double dot equals minus L square over mu r cubed minus del V over del R. Now you can see that this equation here, del V by del R is like a force, right? If you remember, a force for a conservative field, force is defined as minus gradient of the potential, and this is the gradient of a potential. So the second term is like a force, and what is this first term? We don't know what this first term is. So actually, one way of looking at this first term is, if we go back to our Euler-Lagrange equation, let's look at the Euler-Lagrange equation all over again. The Euler-Lagrange equation, the first part is simply mu r double dot, right? Mu r double dot. And the second part is del by del r of the Lagrangian, which we can also write as, because the first term here does not depend on r, it depends on r square. So we can write it as del by del r of the remaining quantities, and the remaining quantities is L square by 2 mu r square minus v of r. Okay. Now, and in this form, you can see that this is of the form mu r double dot. So that is like mass times acceleration equals uh, the derivative of something, right? Mass times acceleration is the derivative of something. And this would be our force essentially. Okay. And this force, I think I'm missing a term somewhere. Okay, I think this is correct. That is correct. This is correct. Okay, so this part is the gradient del by del r of some quantity, the gradient of some quantity, which is called the V fictitious. This is called the fictitious potential. Okay, the actual potential that which is being applied is V of r, but this V of r gets modified by something which is L squared by 2 mu r square, and this is a fictitious potential. And the combination L square plus 2 mu r square minus v of r, this is called the fictitious potential. And in fact, one should write it with a negative sign if you really want to be careful about minus of v of f is equal to minus gradient of v. You should write it with a negative sign here. So this should be a plus and this should be a minus, and this should be a minus sign. Okay, so we keep moving on. This is our um, this is our equation of motion, where v fictitious is equal to v of r plus L square by 2 mu r square. Okay, there's one more thing that we should discuss before we move forward, and that is energy conservation. Energy conservation. And we can find actually energy conservation using our this equation. We can actually use this equation here to figure out energy conservation. So let's do that. you see that we have this equation mu r double dot equals minus del by del r of L square by 2 mu r square plus V of r. Now what we can do is we can multiply both sides by r dot. So multiply both sides of this equation. Just to be careful, let me write it down. Multiply both sides by r dot. If you multiply both sides by r dot, you will get mu r dot r double dot equals minus of r dot del by del r of L square by 2 mu square r square plus V of r. Now you can check that mu r dot r double dot can be written as d by dt. This can be written as d by dt time derivative of half of mu r dot square. Okay, you can check that that is going to be correct. And again, dr dot, if you write r dot as d by, you can write r dot as dr by dt, and then you have del by del r of L square by 2 mu r square plus V of r. So this can be written as essentially d by dt of L square by 2 mu r square plus V of r. So we have d by dt of half mu r dot square equals minus d by dt of L square by 2 mu square plus V of r. Now you take everything to the left hand side, which will give you d by dt of half of mu r dot square plus L square by 2 mu r square plus V of r equal to 0. And you can check, remember we had mr dot squared theta dot equals L, the angular momentum conservation. Or mu r dot square theta dot, sorry, the angular momentum equation was mu r square theta dot equals to L. That was the angular momentum equation. And if you substitute that into here, you will get d by dt of half of mu r dot square plus r square theta dot square plus V of r equals to 0. And this is nothing else but the kinetic energy. This part is the kinetic energy. This part, of course, is the potential energy. So you have d by dt of kinetic energy plus potential energy, which is the total energy, equal to 0, or energy is conserved. Okay, so you can show, of course, that the energy of this whole system is conserved. Now that we have shown that the energy is conserved, let's go back. This is our equation of motion. We are really interested in the equation of motion. We want to understand how the object would behave when it has this equation of motion. So in fact, we have two equations of motion. Two equations of motion. Okay, what are those two equations of motion? Well, one of them is one of the equation is simply the angular momentum. So m r square theta dot equals to L, or conserve. This is our one equation of motion. This is the equation of motion for theta. And the other equation of motion is, and I keep making this mistake, this should be mu, not m. And the other equation of motion is that mu r double dot equals minus del by del r of v of r, the central potential, plus L square by 2 mu r square. Okay, and this is the equation of motion for r. So these are our two equations of motion, and in principle what you do is the second equation, the r equation, does not depend on theta. So you first solve this equation analytically, or once you have a functional form of v, and then once you get the solution for r, you substitute it in the first equation and then solve it equal to d. So in principle what you need to do is you solve this differential equation, the second differential equation, which can be written the second differential equation, you solve it in terms of r, and then you substitute it for L, and then your theta can be written as L over mu r square. Okay, that is theta dot. So you can integrate both sides with respect to t, and once you integrate both sides with respect to t, you will get theta equals the integral L over mu r square dt plus some constant. Okay, that will be your equation for theta, and the equation for r you can obtain from here. Okay, but this is a little bit complicated. So what we are going to do is we are going to look at, first we'll try to understand how we can solve for, or how we can get some understanding of what the force or what the motion would look like just by looking at this quantity. Okay, so we are going to just do some kind of a pictorial solution. Okay, so how do we do that? We are interested in this potential V fictitious equals V of R plus L square by 2 mu R square. Okay, now remember that if you have some potential, for example the simple harmonic oscillator, right? If you had the simple harmonic potential Vr as a function of r, then we know that the motion is simple harmonic because the minimum of the potential is here, let's say at r0, and if you take an object and put it here at some position which is not equal to r0, then this object, because it wants to go down, it wants to reduce its potential energy, so it would go down, and as it goes down, as it loses its potential energy, it will gain in kinetic energy. So when it comes at the bottom here, it will have the lowest amount of potential energy, but it will have now gained some kinetic energy. So because of that kinetic energy, it will have some velocity, and it will keep on moving, and it will go up the hill again, where it will lose its kinetic energy but gain its potential energy. It will keep going up to the place where all its energy has converted into potential energy. The kinetic energy is zero, but now that it has some potential energy, it will turn around and move back. It will keep on oscillating. And how far up it will go will depend on the total energy it has. So that's where we started. So if we started with this some amount of energy E, then it will go down. And as it goes down, the kinetic energy plus potential energy has to be conserved. And as it goes down, the potential energy turns into kinetic energy, And the kinetic energy, as it goes up, the kinetic energy turns into potential energy and so on, and it keeps on oscillating in this potential well. So we know this from our previous classes. We can apply a similar idea to understand how an object would behave under any fictitious force. So before we do that, let's try to understand how L square plus mu square, what would be the potential if we had, let's say there was no external potential, then what would the V of R look like? Well, we can clearly see that if there's no external potential, then L square by mu R square, if we are just thinking about the dependence on R, not R vector, but just the magnitude of R, well, this would be something like this, right? This dependence would be something like this. 1 over R square dependence. Now, we have an additional term V of R, and let's choose V of R, something that we are more familiar with, that we want to work with. Let's choose that V of R as gravitational potential, for example. So if we choose V of R to be gravitational potential, that would be Gm over R, something like that, right? Minus Gm over R. Now, how would Gm over R look like? Well, if this is R square, then Gm of R minus of Gm of R would be a little bit more shallower, something like that. And if you look at the fictitious potential, V fictitious, which is L square by 2mr square minus Gm over R, that is the combination of these two curves, so 1 over R square and 1 over R, and that looks something like this. So and the reason it looks something like this is because for small values of R, you can see that 1 over R term is dominant. So the positive term is dominant, and hence for small values of R, the fictitious potential is going to be positive, but for large values of R, the negative term is going to be dominant. So for large values of R, you will get this 1 over R term to be dominant, and in between you will get some kind of a minima, right? So that's how the potential looks like, and we want to study how the motion of the object would be under such kind of a potential. So let me redraw this potential. I'm going to redraw this potential. This potential is something like this. Okay, that's the type of potential we have. Now, how the object will behave would depend on how much energy you provided, exactly the way we had in our simple harmonic oscillator, when the energy was determined how high the object would go in the potential. So let's say the energy was here. Let's say that's the total energy that you provided, and let's say we started with an object at this point. So you start with an object at this point. It has no velocity right now. It has all its, because v plus t has to be conserved, all its all its energy is in terms of its potential energy. Now this object cannot go towards the left. Well, why can't it go towards the left? Because if it goes towards the left, which means that the potential energy will have to be larger than the kinetic energy. Sorry, the total energy. If it goes towards the left, it goes in this direction, it has to climb up the potential. So its potential energy will be larger than the total energy, which means that the kinetic energy has to be negative. But that is not possible, because if kinetic energy is negative, then the velocity, kinetic energy is a v square term, right? So kinetic energy is half of mv square, but v cannot be imaginary. At least the type of object we study, if kinetic energy is negative, then this has to be negative, which means that V has to be imaginary. So that is not allowed. The only thing that can happen is this object can move towards the right. Okay, and as it moves towards the right, which means that as it moves towards the right, its potential energy is decreasing, decreases. The potential energy gets converted into kinetic energy. At the bottom, it has the lowest amount of potential energy and the highest amount of kinetic energy. And then as it goes up, because once it reaches the bottom, its potential energy is the minimum, but it still has some kinetic energy and it was moving towards the right. So it will keep on moving towards the right. Now its kinetic energy will decrease, potential energy will increase, and it will go on up to it reaches here, where it will have some amount of potential energy and some amount of kinetic energy, and it will just keep on going towards the right forever, and it will never come back. Okay, so that's the case when the energy is larger than the asymptotic value of the potential, or the V infinity. Now we can also think about this, the same situation when the object didn't start from here, but let's say the object actually started from really far away. So the object started from really far away, and it was given some velocity towards the left. So it has some kinetic energy and some amount of potential energy, and we can choose that potential energy to be zero. We can choose V infinity to be equal to zero or nearly equal to zero. So let's say at that time all its energy was this kinetic energy, and then it started coming towards the left. So it will keep going towards the left. Actually, as it comes more and more towards the left, it will favor it, because its kinetic energy keeps on increasing, the potential keeps going down, so it keeps getting attracted. It keeps getting attracted, and it goes in the well where it has the maximum kinetic energy. And then here it will have the lowest amount of potential energy, and once it reaches here, since it still has some kinetic energy, it will keep going up this potential well. It will keep going up till it reaches this point here, where it will have the maximum amount of potential energy. All its kinetic energy would have converted into potential energy. So here it will stop. It cannot go any further, as we argued earlier, because if it goes any further, its kinetic energy will become negative, which is not possible. So this is the maximum place it will reach, and then it will turn around and go back. It will turn around and go back, and then as it goes back, it will go away to infinity and never come back. So this is an object that starts from infinity, comes closest till this point, then turns around and then goes back. This would be the case when the energy is larger than the asymptotic value of the potential. Okay. Now we can argue similarly for other cases. So the next interesting case would be for the same type of potential. The next interesting case would be, let's say the energy is lower than the asymptotic value. Okay, so if the energy is lower than the asymptotic value, the object can never start, for example, in this position. It can never start in this position, because that would require its potential to be larger than the total energy of the system, which means that the kinetic energy has to be negative. So it is never allowed to be in this position. The only position it's allowed to be is this value of r, let's call this r2, and this value of r, let's call it r1. So these are the values which are allowed. Everything else is not allowed. This is again very similar to our simple harmonic oscillator case, where the only values of r which were allowed was in this region. The other values of the radius was not allowed. And the behavior would be exactly the same like the simple harmonic oscillator. If you start an object in this position, it will go towards the left, it will gain in kinetic energy, it will lose its kinetic energy as it climbs up on this side. Here it will go to zero, the velocity will go to zero, turn around and move back. So the object will just keep on oscillating between these two ends. Now as you keep lowering the energy further, you will reach a stage, I can just draw it here, you can reach a stage where the energy is right equal to the minimum value of the potential. Let's call this energy E3. This was E2. And this will be the minimum value of energy which is allowed in some sense. And once you have this amount of energy, for this case, there's only one value of R which is allowed. And that value of R is right here. So as the object moves, all its kinetic energy would be because of, remember in the kinetic energy we had half of mr dot squared plus r squared theta dot squared term. But because r is constant, the radius is fixed, the first term is actually zero. So all the kinetic energy which is coming from is from half of mr squared theta dot squared. So because of the motion in the angular motion of the object, that's why you get the kinetic energy, and the potential energy is the minimum in this case. And in this case the radius is going to be fixed. So if you look at the object, if you look at the r coordinate in terms of, let's say, the xy, if you look, remember we are studying object in a plane, so if you look at the object, the radius is going to be fixed and the object only moves, the object has the same radius as it moves around, so this will be like a circle. So this trajectory of the object would be a circle where the radius is fixed all the time and it just keeps moving with some velocity theta dot. Okay, for the case where you have E2, where there are two different radii, the motion would be it starts from some radius, it goes down, then it goes again up. For the special case where the trajectory closes on itself, which would be the case of the planets, this looks like an ellipse. The trajectory looks like an ellipse. For the special case where the trajectory closes on itself, it's not necessary that the trajectory closes on itself, and we can discuss about it in some other time. This is getting too long, so I'll talk about this in some other time. For the time being, let's just remind what we did today. We started with central force motion, where there were two objects, M1 and M2. They interacted with each other only in terms of their relative position. There was no other force. The relative position only mattered. So we write down the kinetic energy and we write down the potential energy, which depends on R1 and R2 right here. After that, we did a change of coordinate. So we went from R1, R2, which was the vector of the two objects, to the center of mass and the relative position, R1 minus R2. Once you do that, you massage through the equations, you get the Lagrangian that depends only on R dot, capital R dot. It does not depend on capital R, which is the center of mass. So that provided us, or that told us, that the momentum is conserved. And we reduced the problem from 6 independent coordinates to only 3 independent coordinates, which was the relative position R. Then we realized that because it only depends on the relative position R, there is a spherical symmetry in this problem. That spherical symmetry results in conservation of angular momentum, which allowed us to change this problem from 3 dimension, which were the 3 relative position of the vector r, to only 2 dimensions. So we only cared about now the radius r and the theta angle. And then this Lagrangian, we again realize that theta is a cyclic coordinate. The Lagrangian does not depend on theta, it only depends on theta dot, which gave us that the magnitude of angular momentum is conserved. Once we had that, we converted this into this Lagrangian only in terms of r. Now that this Lagrangian is only in terms of the radius vector r, we can find out the equation of motion. We realize that the equation of motion can be written as the gradient, as mass times acceleration is the gradient of some fictitious force. We also realized that the energy of this system was conserved. And then what we did was, after we proved energy conservation, we used pictorial methods to find out how the motion would look like. So the fictitious force was the actual potential, the central potential, plus this additional part that comes because of the, you can think of it as centripetal force. And then the net potential is, the net fixture potential is the original central force potential plus this additional part. So if you want to study it, is very similar to studying a system for just one potential. So if you have a potential well, like a simple harmonic oscillator, for a fixed amount of energy, the object goes always along the gradient of the potential. So if you give it some fixed amount of energy, the energy will convert from potential energy to kinetic energy, and the object would kind of oscillate if we had a simple harmonic potential. We can use the same idea when you have the fictitious potential, where you draw the combination of both these terms, the central force potential and the L squared by 2 mu r squared. So that's what we did. We looked at the net combination of the potential for the case of gravity. For the case of gravity here, and then we analyze different values of energy. So if the energy is larger than the asymptotic value of the potential, then the object would be like a comet. It will come very close to the planet and then move away. If the energy is lower than V infinity, then the object will have bounded motion. This would be like an ellipse if the energy is lowered, but it intersects this potential curve at 2 points. The object or the motion would be like an ellipse, but if it intersects only at 1 point, then it will be a circle. Okay, so we'll stop here and we'll talk about under what condition you get ellipse and a circle in the next lecture.